Okay. Well, hello everyone. As Susan mentioned before, my name is Oscar. I am a postdoc working with Susan here in Oxford. We have been working for a while. And I will be presenting practically what I have been doing in the last 3 years, and it's trying to use the multidimensional Gaussian process approach to model the stellar signals in spectroscopic time series, which is radial velocities and activity indicators. So the reason why we are wanting to do this is because we want to find planets, but unfortunately, or fortunately because it's more fun, stars are not uniform disks of light. So they have spots. And some months ago, I was reading a book by a Latin American author, and he found a nicer way of saying this. And he was saying not even stars escape from the ring of life. So stars are not perfect. And what I mean when I read this kind of things is this: that stars, this is an image of the sun. The sun has spots on the surface. As the sun is rotating, we can measure quantities of the sun. In the top panel, we see how the irradiance change in time, and in the bottom panel, we can see how radial velocity change, and we can see that as the spots appear and disappear on the stellar surface, these quantities change as well. So it's not everything flat. So measuring planets are affected by these kind of things. So a disclaimer: in this talk, I know that there are different ways in which stellar activity can manifest and create signals. In this talk, when I'm mentioning activity, I mainly mean spots. So you just make this disclaimer. So there are some other really interesting things that I might not be covering in my talk. So induced radial velocity. So we know that we have spot on the stellar surface. As the spot is moving around, this makes a change of flux and also a change on the shape of the lines. And when you extract the radial velocities, this creates an apparent radial velocity that is not true. It's not that the velocity is changing, it's just like the activity of the star is making that the measurement that we are doing of the radial velocity manifests in the time series. So here is like another animation that shows more or less the same. So we have here like some kind of pattern of spots appearing on the stellar surface, and we see like this kind of signals testing as a radial velocity. And since we want to use the radial velocity to measure planetary signals, this is the big problem. But fortunately, we can, from the stellar spectra, we can not only extract radial velocities. There are some other observables that we can also extract from the spectra that we collect from the stars. For example, people can measure how the lines deform, or how intense some lines can get. And when you measure this together with the radial velocity, you came out with another time series of some other quantities that are called activity indicators. So this time series practically contains information about the stellar activity, but it doesn't contain information about the planets, because the planets usually don't affect the activity indicators. So here I show an example of the same images that I put before of the sun. Here we have the radial velocities. Here there are two activity indicators that I will not describe what they are. They are just quantities that were measured from the same spectra. They measure the radial velocities, and we can see that they have some kind of they are also changing as well as the radial velocities. So these activity indicators can give us information about how the stars, how the stellar activity manifests in the radial velocities. So if we go to try to see how these spots affect the stellar activity, we can use a code like SOAP2 and try to make toy models to see how the spots affect the time series. And the first thing that we can see is like every time series is affected in a different way. Here in the middle panel, we have flux. Here we have radial velocity, and here we have the sector. So this is a toy model, really simple. You put a spot that doesn't change size or position. It's just rotating on the stellar equator, and you have something like this. And if you look closely to the shapes of this time series, they look totally different. In the time series that you're seeing is different in the flux, in the radial velocities, and in the activity indicator. If we look a bit more carefully, we can see that this function behaves as a function that we can call g. If we look to the radial velocities, the radial velocity, it doesn't look anything like the flux, but it looks like the derivative of the flux. It looks like a signal that you can compute by taking the time derivative of this function. And then when you go to the dissector's time, you will see that is also behaving as the derivative of the flux, just like inverted, just with the negative sign in comparison with the flux. So it looks like there is a relation between the stellar activity that you see in the radial velocity with what you see in the activity indicators. It's just like the relationship that is not linear. It's not like you can think that the same signal that you see in the RVs is the same signal that you see in your activity indicators. So this was taken into account by Suzanne like 10 years ago, and it's like they found that the RVs have something that is called the FF prime behavior. That is like the RVs behave as some kind of combination between like the flux, well, the square of the flux, which is like the linear path of the flux with no derivatives, and also has some dependence on the derivative of the real of the flux. So if we want to measure if you want to describe how the real velocity is behaving by observing the flux of the star, we need to take into account the derivative of the function that we are using to describe the flux. So this idea was taken further by Rajpaul, and in 2015, that is what Suzanne mentioned before. And the idea was taking this, in which we are assuming that the RVs are behaving as the derivative of some other time series, and creating this kind of approach in which we have like the real velocity can be described by like a linear term and derivative term. Some activity indicator, it can be describing only like the function that is describing more or less something like the flux, and then some other activity indicator that is the sector that can be described by the activity by the same function, but also the derivative of the function. So I mean, here in this talk, I will not go and describe what Gaussian processes are, because there is no time. But I mean, if you know what GPs are, then this is the multidimensional Gaussian processes. If you don't know what Gaussian processes are, just imagine that we are trying to extract a function that is behaving is having the same more or less shape in different time series. So this is like the two ways in which you can imagine it without being afraid of not understanding Gaussian processes. It should not affect the outcome of this talk. So the big idea of this talk, as I said before, is to have one GP to rule all the time series. So this is what we want here, and with this under the assumption that the relation between the stellar signal can be the same in the radial velocity and in some other activity indicators. Of course, this framework has been expanded I wrote a paper that was just published at the beginning of this year. There are some other two papers really good as well. I think that reading the Benetti paper, these two papers, and the Vinesh paper 2015, they all complement each other really well if you really want to go deep to understand how the multidimensional framework works. But the big difference here with comparison with the other paper is like in this way we are just doing more activity indicators. You can start to add all the activity indicators that you want, and you can just turn on or turn off like derivatives by fitting like parameters to 0. So it will be only like here. So I will encourage you to go and see the Benetti paper, because practically all the conclusions that I will be showing, we are discussing them in the Benetti paper. So I really invite you, even if you don't use Benetti, I really encourage you to read it. So I hope that at this point I convince you that it's important to take into account the derivatives of the function that describe the flux or that describe some activity indicators in order to describe the stellar activity. But of course, this brings some kind of problems when we are trying to go to the equations to describe the models. So, for example, the two things that before that, I want to tell you that now we can, if we really believe that there are activity are signals that are behaving the derivative of a function, we can describe. I like to describe the time series that there are two kinds of time series. Some ones that I call photometric-like activity indicators. By this, I say that these are time series that behave only as the G function. And for this, I have some examples, which is like the H and K calcium lines, full width and maximum, or differential line width. There are some quantities that behave as if they were the flux. While there are some other kind of time series that I like to call RV-like activity indicators, that it can be like the radial velocity or the bisector span. There are time series in which you also need the derivative of these quantities in order to describe how they behave. So if we believe this, we need to start to see how the functions that describe these kind of things behave. So we usually use this. I usually use this function that is a quasi-periodic kernel, and practically we can divide it into parts. The part that is the periodic part, and the other part that is the quasi part. That this doesn't make it totally periodic. So we can find some kind of parameters here. We can find the period, so the periodic part that tells you how much the period, the rotation of the signal that you want to measure. Then the inverse of the harmonic complexity. This number tells you the smaller the number is, the more harmonic complexity your signal will have, and this means that the more harmonic complexity you will have more wiggles for every period. And then you also have another parameter that is I didn't change the name. Okay, I will change it when I share the slides. But this is the time scale evolution. So the time scale evolution tells you how much some kind of signal repeats for how many days. I will not describe more how these things relate with physical quantities. If you want to know that, I will encourage you on Wednesday, listen to Belinda Nicholson, because she will be talking more about how these signals can relate with the physical quantities of the stars. So but the thing is, like, if we want to use this to describe our activity indicator, if we want to describe how the derivative works, the derivative works something like this. So when we want to include this in our covariance matrix to compute Gaussian processes, so now the periodic part is this, the quasi part is this. So if we want to imagine this enters in the equation, of course it has more complexity to the functions that we are using to describe our stellar signal, and this has really interesting behavior in the time series that we have been observing lately and in some stars, and they are really fun. So the first one is that what happens in the high harmonic complexity scenario? What happens if your signal, if your star has a lot of spots, is rotating fast, whatever, and then you have like a really high harmonic complexity? Well, you will see that the time series that behaves as the derivative, in this case a radial velocity-like time series, compared with a photometric-like time series, you will see that it has a higher apparent harmonic complexity, which is much more complex than what you see in your activity indicator. So this is really important because when you are using a light curve to train your GP with the hyperparameters, you might be giving the wrong information because you might need a higher harmonic complexity in order to model the signal that is in the real velocity. So this is one of the first things that we started to observe. The second one is in the other extreme, in which you have low harmonic complexity scenario. In this case, when you do the math, you see that practically both signals behave as sinusoidals, but the RV-like time series behaves, they have more or less the same shape, but there is a small shift that you see in the stellar signals. So here I also have like an animation in which I created this kind of signals in which you have the harmonic complexity, the activity indicator-like signal, and then you have the radial velocity lifetime signal. They both look practically the same, but you have a small shift in which the radial velocity seems to be a bit high, and this kind of shifts have been observed. Actually, Annelies will talk about this. I'm looking forward to see that. So it's very important to see that if we believe this, that the RVs behave as the derivative of a signal that describes the activity indicators, things are a bit funny. It's not the relation is not so linear. So I will now show some the applications that we have used in order to measure some planetary masses using this multidimensional approach. So the first one is my first planet with Gaussian processes. So it's K2-100. When I arrived here to Oxford, Susan told me, look, there is this data set. Do you want to give it a go to see if you can model it? Then I was like trying to understand what the Gaussian process were, trying to code it in the code. And finally, I was able to do it because before previous attempts to measure the mass to detect this planet in the RVs were like, we're not able to detect a 3 sigma confirmation of the planet. I was able to model the data with the multidimensional Gaussian processes, and whoa, the planet was there. So this, I mean, I will not go into the details of the planets because this is not the objective of the talk. But if you see something really important in this, is like here we have the activity indicator, that is a photometric-like activity indicator. Here we have the radial velocities. And if you look carefully to this plot, this is just like an example with real data of the toy model I present in the first slides. So we have some activity indicator that is behaving like a flux, and then we have the radial velocity that is behaving as the derivative of the function here. So here really using the activity, the multidimensional Gaussian processes, and using the derivative of the signal really help us to measure the planetary signal in this data set. So this was really encouraging. This was like showing that it was possible to detect planets in RVs of really young active stars. So we continue with this. And then another good example of this is QI 516, which is another young system in which we have the same kind of behavior, in which, I mean, here it's not so easy to see that one is the derivative of the other because it's like the signal is a bit more complex. But the important about this in this paper is like we were able to combine radial velocities and activity indicators from different spectrographs. So we use they all in the optical. We are using the same wavelength because we don't want to get into troubles. And then we have here the radial velocity behaves as a derivative, again, of this function. And also like the amplitudes of the activity that you see in the activity indicators in different spectrographs and in the RVs, they look more or less the same. So this shows that we can also use this approach to model stars in different stellar signals in different kind of spectrographs. And like one of my favorite ones is like this one that we just did some kind of some weeks ago. That is EUMIC. It's a EUMIC in which we have like a stellar signal is around 50 times larger than the signal of the planet. So here you can see the points. Well, the observations are the 2 points, and then we have the model, and then the planets is this yellow line that practically looks flat in this animation in which we put the same kind of scale that the stellar activity, but we are able to detect the signal, and then we are using here another activity indicator that is helping us to measure the signal. It's really this was like a really good work that we did, and we managed to really do this. And I will manage later. I will in some slides ahead. I will mention you how we really what we did in order to plan this. But we have also found that this what happens with this works well with young systems in which we know that we have big spots and they are like doing their they are like affecting velocities. So there are also some other systems which are a bit older. In this case, we have TOI 1260, in which we have like 2 planets. We also have like the stellar signal here. And something that we can see is like there is not a really high harmonic complexity in this system. There is a low harmonic complexity here, but we can see that the stellar signal in the RVs is like a bit ahead from the signal in the activity indicator. So we are seeing this thing that we were predicting in the with the modeling that we were doing. There is another example. This is not like a super secret. It's just like I didn't ask the first author if I could present this here. So it is another example in which we have the stellar signal in the S-index, in the full width maximum, and the radial velocity. And it's really fun how the stellar signal has exactly the same shape in the S-index, in the full width maximum, and in the radial velocity. But the radial velocity is really small because this star has a lot of planets. So the planetary signals are more. Actually, we use this approach in order to convince the referees that it was valid to approach the stellar signal as a sinusoidal because there is no harmonic complexity here. There is nothing to really worry about. And well, a bit more. And what is the plans to do with this? The first thing is that in the Pianeti paper, there is an extra thing that we are publishing that is called Citlalatonac, that is in honor to the Aztec god who created stars. And actually, this code is what it does. It's creating synthetic stars in which we are creating a synthetic time series with activity indicators and arrival velocities. We use this to have the observations for EUMIC. We were using like all the information that we have from the archive. We create simulations to see we were able to detect the EUMIC planets. We showed that, so we wrote the proposals, they gave us the time, we observed, and now the paper is out. So it has been like a really fun process how we use these tools. So I encourage people to use these kind of tools to plan observations of active stars because it's also important to take into account the activity indicators. We are also doing another paper to see to simulate hundreds of time series to see if we can detect the hyperparameters. To see how many points we need in order to measure planetary for a given set for different kind of stars, and if we can recover the hyperparameters from simulated data. But this is just like there are no plots still for this, so it's just like what are one of the plans that we have. Another very important work that is being done here in Oxford by Hao Chan is measuring periods from a sample of stars which have been intensively observed by HARPS. And he's trying to measure the period for stars with different spectral types. So also stay tuned to see what Hao Chan can find. And also the next thing I want to do is to do injection tests in the radial velocities of the sun in the HARPS data, in the HARPS North data to see if we can recover. This is like a really old plot of the first attempts I did in which we were recovering more planets using the multidimensional approach than some other approaches. But this is just like a sign that this is a plan, but this plot don't listen too much. It's just like that is there. And well, this is how I end. This is my take home. Well, there is a relation between activity indicators and radial velocity, but it's not linear. Be careful. Use your activity indicators to model your radial velocities, but really carefully. Stellar activity has different shapes, different phases in different time series. So this is something that is worth to take into account. it looks like FFF-like approaches work to model stars which have like big spots, which are spot dominated. GPs are really powerful, but use them wisely, please. And then also I invite you to check the Pianetti paper, the Pianetti 2 paper, even if you don't use it, because all the conclusions that I'm putting here are described there. And I end with this. Thank you.
I was just going to say one thing is we especially encourage, I meant to say this at the beginning, but I forgot. We especially encourage questions from graduate students, and we're going to try and pause for a minute at the beginning of each question session to give people time to think about their questions, because I know sometimes it can take a little bit longer. So please, if you're a grad student, feel free to raise your hand straight away. If you're a more senior person, please just give time a little bit.
Hi, I'm Constrain. Hi, Oscar. I've actually worked with David, your old advisor, and used your code before, actually. This is a very naive question, perhaps, but it seems like this approach requires that you also have a flux-like activity indicator or flux-like time series in order to take advantage or leverage the multi-GP approach, right? What if you only have RV-like indicators? Can you still like leverage some of that multi-dimensional power out?
So is the question?
This is the question, Oscar, just in case.
Yeah, I think the question is if it's I am using radial velocity with activity indicator, but what happens if I only use activity indicators, right?
No, I think the question was, what if the only activity indicators you have behave in an RV-like manner? What if you don't have a photometric light?
Okay. I have done this test before, and if you do this, it looks like there is some kind of the system cannot be solved because you need something that is really regulating the shape of G in order to be able to know what the derivative of that would be. But if I have done testing which you have RVs and bisector, you left free of the amplitudes for the two-time series, and then at the end the hyperparameter gets crazy because actually you can have like an infinite number of combinations that the G function is not really well constrained. So every time I do this, I always ensure that there is one photometric-like activity indicator that is constraining the shape of G. Yes.
Sorry, I think.
So one thing that's amusing to me in this kind of situation, so it's obvious that this model is excellent. It's also obvious to me that in addition to RV, you have something like 70 to 300,000 other measurements you're making at the same time, which is every pixel in the spectrum. Every pixel in the spectrum must act like a mixture of these indicators.
Yes.
So is there an approach in which you just model absolutely everything with your two GPs?
I mean, it could be possible. It could be really computationally expensive. So, I mean, I think it could be a way to explore further which activity indicators to use and maybe to extract better activity indicators, because this is something that I want to look further. I think it looks like maybe using more information will be always better. I have done tests in which you start to add more activity indicators, and at some point there is like there is no improvement on the planet recovery rate. So maybe it's possible to try to see if you can find more data, more information from the spectra, and maybe you will be able. But I think it's something that is worth to check. But I have not looked to more than 3 or 4 activity indicators at the same time because it's expensive, computationally expensive. Please.
All right, I'll try to speak so that the microphone can hear it too. Thank you, Oscar. It was a really nice talk. One of the things I have a hard time wrapping my head around in terms of GPs is how we evaluate the error on the parameters we get out in the end. So I know you've done some stuff on trying to basically get an error, like a realistic error on the mass. That's what I'm interested in. So can you say something like what do you think is the best approach for getting a realistic error on the planet mass in the end, and what kind of approaches would you recommend to people?
Well, what I usually do is, for example, for the eumic planets, we detect the signals like 3 sigma, like in the limit of detection. And what I did in order to be sure that the error bars, what we were recovering, had more or less of sense, I did a lot of simulations to try to see if what I was getting had sense in some kind of other conditions, and this is like what I did.
Oscar, can you maybe just say a little bit about how you embed the model in a Bayesian framework with an MCMC? Just
What I usually do is practically just put the GPs go within a likelihood, and then I try to maximize the likelihood. And then with this, I use an MCMC approach in order to do the maximization, and then this creates like the posterior distribution, and this is how I am extracting the error bars from every hyperparameter.
so you essentially marginalize over all the other parameters when you're evaluating the posterior on.
I mean, I do exactly what you will do in a non-Gaussian approach. Gaussian process approach. You use the marginalize. You solve. You find your posterior distribution for the parameters you are fitting, and then you believe that.
I think I'm asking the question because I'm a little worried about basically overfitting, so that.
This is also one of my biggest fears.
And I think especially in these systems where we know the periods of the planets because they're transiting. I don't know. I'm thinking a lot about like how to test the hypothesis of is there a planet at all or something like that, right?
Like in a blind RV search.
Yeah, or like how to make sure that we're not overestimating the mass of a planet if we only have a fairly sparse signal, for instance. So if our error bars in our data basically is large compared to the signal we're looking for. I don't know. We can take this off.
We can discuss this. What I avoid I have seen that overfitting is more a problem with Gaussian processes when you have like a really bad sampling. But if you have a good sampling, then things start to.
Okay, that's a good point. Yeah, thanks.
But cross-validation is definitely relevant.
Thanks so much, Oscar. Very nice talk. I just have a question I think is more related to the first two. I'm wondering, in your typical analysis, what guides the choice of the activity indicators? Because so there was this question about whether or not G and G, the derivative is constrained, but then we can go all the way and model the whole spectrum. But I think we can think about a dozen activity indicators very easily. So what guides your choices so that in a paper you choose 2 or 3?
I am more pragmatic. I don't have like I take the activity indicators, I analyze them, and what seems that there's a signal in there is what I use. And something that I have tried to use is the correlation, like check the correlation between the RVs and the activity indicators. But correlation seems not to be a good way to select activity indicators because, for example, you expect that RVs and the sector they both more or less have the same dependence, so they have a strong correlation, but the sector might not be the best one. So, but if you make a correlation between RVs and calcium lines, you will see that the correlation is really strong, but you will see that the calcium lines have a lot of you can see the stellar signal there. So what I'm doing now is I go to analyze one activity indicator, like with one Gaussian process, see if I can recover the hyperparameters, then try to do the dimensional Gaussian processes and see if the hyperparameters that I'm getting are consistent. So, and this is like a good way to check that everything is working. And usually I like to see the same signal into activity indicators. This is telling me like, okay, it looks like I have an idea of what is the stellar signal there. But also I tried that when I model it together with the RVs, I obtain the same. So, I mean, there is no like a rule. Something I found is like, for example, for F and K stars, the calcium lines work really well, but for AUMIC that doesn't work, it didn't work well. So we need to go for some for the differential line width to like activity indicator. So at some point, I mean, we would like to have a list of, look, your star is this, use this activity indicator. We are not there yet, but this is like a good. But I mean, by now we can be pragmatic.
Just before the next question, can I get Jean-Baptiste to come and set up? And then, yeah, we'll just got 1 more minute, 2 more minutes.
Okay.
Just for this last question.
We'll keep this then.
So just at the back of the room and.
Yeah. So when you mentioned the photometric-like activity indicators, you mentioned the calcium lines. Is the expectation that any traditional activity indicator, calcium H-alpha, calcium infrared triplet, is going to be photometric-like because you are measuring the flux within the line? Or is it inherent to the way you're measuring the activity or what you are measuring? Are different lines likely to sometimes be more RV-like versus photometric-like?
Yeah, I mean, the fact that an easy way to see which activity, which time series will depend on the derivative is how much they depend on if the spot is in the blue shifted part of the star and in the red shifted part of the star. For example, the flux, if you have it in the blue or in the red shifted, it will not really affect, I mean, you will have the same decrement of flux. But if you have RVs, like the induced RV will be different if the spot is in the red shift part of the star or in the blue shift part of the star. So if you think that you have an activity indicator that cannot feel in which part of the two hemispheres of the star is, then this will be likely a photometric-like activity indicator. So, for example, like the Gaussian lines, it doesn't really matter in which part is it. You only get like the flux there.
Thank you.
All right, let's thank Oscar again, and you can.